we have a hot topic. I'm Lingguo. I teach methods courses in the College of Education, and I'm going to share with you today and where and how I wasted all my time. My job as a math educator is to work with the teachers in K-12 and across campus and in many departments to think about ways to teach math, to enjoy math, and to extend things so that children can enjoy mathematics in K-12 and beyond. Think about math education in the schools right now, today. We have millions of children going to school in 3rd grade, 4th grade, 5th grade, all the way up to high school, after which they come to this building or elsewhere to continue their explorations. What kind of math are those children getting today? How math is taught to children? Why sometimes we, the college professors, are happy about the math those students bring to this campus, or more often than not, we are not that happy with the outcomes. In what ways can we reimagine mathematics education in school? That's my job, and I do work with computer scientists, mathematicians, including those in this building, and chemists upstairs. So I do have a PowerPoint, which I don't always like. So it's a personal reflection on math, art, science, and pedagogy. The big term, pedagogy, is just how we teach. How can we introduce the idea, for example, a group, symmetry group, to children if they're interested? Or calculus, or algebra, or geometry, or 3D space. I do a lot of origami, making with the straws, pipe cleaners, and sticks, bamboo sticks. Recently, I also tried writing programs, apps, Android apps, to kind of play with mathematical processes. In the past 4 or 5 years, and I spent a lot of time reflecting on modeling, 3D modeling, making. And it's an old idea in mathematical education. All mathematicians have made models somewhere in their career. Sometimes they imagine models, sometimes they use wooden models, sometimes they use plastic models. So here's some nice quotes to warm things up. We're all designers. Professors are designers, especially math professors. We design theorems and all the other things that follow. And somebody said the best way to predict the future is to invent it and do unto ourselves. And it's impossible to teach 21st century learners if we have not learned this history. I'm not sure about that, but let's all think about it. Somebody said it. We have to learn some new tricks. Children today are really spending a lot of time on the iPad. It's a good thing or bad thing, I don't know, but they're using it, and they don't want to let it go. I mean, education, we talk about the knowledge design. These are the things we teach our teacher candidates all the time. Knowledge design, we need to try project-based learning, problem-based learning, inquiry-based learning. And we have new standards in the schools, language arts, mathematics, and science. In terms of modeling, we have some very powerful technologies today compared to the technologies they had in the 60s or 70s. And recently, this making movement, laser cutters, 3D printers. I still like my origami projects, but I wanted to extend it a little bit. Tinkering, take something and play with it, and allow your imagination to kind of mix with the math, the processes, and engineering. Perhaps you can make something and sell it for money or for fun, like mathematicians make theorems for fun, right? We rarely get paid for theorems. And we have seen a lot of great people in history. They are interested in using models, design, in education at all levels. Well, as a community, we have really come far and wide in our learning and teaching enterprise. Now we wanted to focus on students and teachers and children, and we come to realize that ultimately teachers and children have to make it happen internally. They have to construct their understanding. I can't just watch you do the math and then magically wish that I could do the math or more. I have to do it, but how? Well, I like this quote. Maybe the best way to understand the circles is to reinvent the wheel. Let's make, in the process of reinventing a wheel, how much math do we have to review and reconstruct? That's the guy behind the one laptop per child movement. I work under this modeling process. A long time working with teachers on modeling. And modeling is recognizing all the standards. If you work with the school children, you know that both in math and sciences, modeling is a recurring theme. And a variety of ways to use modeling. To tell a story about your design, your thinking, what is correct or a failure, or maybe more importantly, with school children and their teachers, create models to have fun with mathematics. Somehow out there we have forgotten to play with math. Take some ideas, turn it inside out, and then fold it back. Let's see what happens. And going back to psychology, there's models into learning. We humans use models to make sense of things. Going back to 3D design, what can we do in terms of 3D design education? So there are so many things you can do to engage students, to role model problem solving. This is how I made those things. I made this many mistakes, failures. I failed, and I made some progress. And then after a whole month, I finally got to this stage. Those stories are kind of educational stories. Maybe you can help teachers and children understand what's going on behind problem solving. All right, so I tried some design ideas with principal teachers. Just some of those you might have had in college algebra or other courses. They create things like this: log rotation, lot of real life things, containers, and they save them as files and they send them to me, and I printed a couple of them for them. Once you design some, you get somehow attached to your model. You want, where's my model? Did you print it for me? I said, okay, I forgot. I'll do it tomorrow. So you have that personal, touch when you create your own mathematical objects. So encouraged by some positive feedbacks, and I decided to really dig into this design for math teachers, see what we can do. From very, very old traditional models to just very playful ideas, and put all these things together. You can see some are really first grade ideas, and some are kind of very tricky. They can be the foundation for advanced processes. They're all available there on Thingiverse. I have a Thingiverse page where I share those things. I try my best to document the history, the culture behind these designs. For example, this one I found, this is called the Devil's Rings. You have it here. It's 3 circles hugging each other. And if you fill the tracks with marbles, it becomes a very tricky problem. These are 3 colors. In how many ways can you put them together? So I also gather some feedback from these teachers or future teachers from several dimensions, the math that are potentially there, and whether it's child-friendly or teacher-friendly or not. And the art, the playfulness, or the pedagogical value. Does it affect the way you approach the topic with children? And I got some ideas, and I'm not going to show all the stats on educational statistics. It's not a science stat. But then I look at the keywords. So these are the things I want those future teachers to really focus on. Make things and relate. Just a lot of ideas scattered in this space. All right. So there's so many stories I can tell. Sometimes just my own frustrations or relearning of something I think I know already. So I focus on two stories today. One is spinning the cube. The other is the case of platonic solids. Who has spun a cube before? When?
Usually whenever I go to the geometer's den, I pick up a Rubik's Cube, hold it between two fingers, and then spin it.
Okay.
Because there's one of your models in there, and I'm trying to show the connection between your model and the actual spinning cube.
Thank you. Yeah.
This is the one you gave me. We keep it on display.
Yeah.
Dr. knows part of the story. Start camera too. I don't hesitate asking questions, sending emails out. I just found this problem I have no idea about. And can somebody help me out there? And I know, and I got responses from math professors a lot. This is great. I also had numerous conversations with Alan Show about these designs. I think I wanted to role model some processes for the children and for my college students. And it's fun. I learned something I thought I did not know. Okay? Little cube. Here's a story. In education, sometimes we ask students to make cubes. And I use origami, the modular origami. That's great. We take 6 pieces of square and pull them up. I did that this morning. And occasionally we use things like this. These are called polygons. With Dr. Mary Wright, a few years ago, we bought a lot for school teachers. Right? So one day we were really looking at the 11 different ways to flatten a cube without breaking the squares off from each other. 11, and you can prove it. Okay? There are many ways to show the exactly 11 cases. Right? And their perimeters are all the same. Interesting. The area, of course, is the same. The perimeter is also the same. So we made some cube, and then talk to kids, and they like to play with things. Somebody tried to spin it. Hey, that's interesting. Let's make it easier to spin the cube. You can try it. It's not easy on the table, on the floor, but some children can spin really well. Just keep trying. So I said, okay, let's put it on a wire. Let's do it. And it goes something like this. Today we have phones. Take a picture. 50 years ago, somebody took a picture like this. I found in literature. There are quite a few books out there. What is it? Some said, it's an hourglass. Well, it's a circle. Well, what do you mean by a circle? This way, the long circles, right? But the whole shape's not a circle. It's something. That's interesting. But what does it look like? Well, we can virtually simulate it. And there are software environments like GeoGebra, which I use a lot. I was involved in the team for a while. And Cinderella, Mathematica, Maple, you name it. You can design the cube and spin it or rotate it around the axis. And you get something like this. And that gives us some kind of evidence. The thing in the middle is not a triangle. It's not an hourglass. It's something like a curve. A curve that's made by this line. So one-sheeted ruled surface. Now, we have 3D printers today, and what if I create a cube? Very easy. Draw a square, push it up, where the word is extrude. You get a cube, and you can easily put some holes in your cube. More. We need this one, so you can put on a screwdriver and spin it. It's easy to spin. Is this one? Somebody spin it for me. Right? Feel it? It worked very well on the screwdriver. I use that to fix the printers. So, now, what is that shape when you spin a cube or similar structures? Can we make one so I can play with it? Can I have one? And you can go to any 3D design environment, make a cube. The cube you design in a 3D design environment is a solid, which can be printed. Things you design in Cinderella or GeoGebra, they are mathematical, they are virtual objects. You can't print them. It's in your mind. All right? Draw a cube, find a major axis, and well, when you spin it, you're creating infinite many copies in space, right? That's exactly what happened. How many copies do you need? 60? Is 60 the same as 20? 17? 57? Because the symmetry. 24 and 8. 24 copies and 8 copies are the same. Well, anyway, play with it. I want 1,000 copies. Just tell the, well, I use Autodesk Fusion 360. Some use Inventors. I want 1,000 copies, overlapping in space. And then you merge them, you get a shape like that. Print it out. Well, that one is given away. Now you have. It's playful. We have it. How do you print it? Well, we can't print things hanging there in space. It has to start from the ground level. You've got a flat, we call it a bed, the printer's bed, the platform. So one way or the other, we have to do some mathematical transformation or split it. So that's what I did. Split it into 3 pieces and print them. Well, get some super glue and put them together. And you can create multiple models. The game is not over yet. What you have in the middle is not as rough as the toy Dr. Kosi is playing right now. It should be a smooth curve. Now you can make it really smooth. But how? That's different. You can try 2,000 copies, change the idea. Going from solid modeling to surface modeling in the design environment. So I'm not going to go into details. Sometimes it takes 5 minutes to figure things out. Sometimes it's 1 second. Sometimes 5 hours. It's a battle between our understanding, the mathematical process, and what is available in the design environment. It's like we go to Lowe's. There's so many tools. Which one should I buy? I don't know. I want to try this. Otherwise, I want to make sure I can return. That's what happens. But it's getting easier, especially for mathematicians or STEM engineers. And what is essentially important is not a cube. It's that thing that's in space. Let's highlight what really matters behind this process. It's that zigzag line. It's based on a cube. Leave the cube behind, focus on that. What if I spin that line in space? What do I get? I get a cage. You can put a cricket in it if you want to. Or this is really nice shape. Remember, it was very expensive to create a model like this years ago. So we created in our minds, but we try to guide the students to recreate those shapes in their mind. But how? It's hard. Some can do it. Some need more time. Others can't. they struggle for a long time, especially the college students I teach. It's, on a daily basis we struggle. How can I get this idea to you? In one semester, excuse me. All right, kids have spinners around if you are your parents. And what if I slice the cube somewhere and put a berry in it and make it easier to spin? Do you really want this, or just a waste of time or plastic? I'm not sure. You can try it. But then how do you put a berry in it? You have to measure that, you have to design it. It's not that hard, it's not that easy. It's just some basic understanding of circles and depth measurement. And there are so many fidget spinners lying there. So just ask for one of them. But it works, spins really well. Those berries work much, much better than I thought. Real smooth. And of course, we want to get some math out. What are the mathematical ideas? There's an angle there. That's very important. Which angle? The angle of these lines in the middle. They're called skew lines. They're parallel to the major axis, but they're not on the same plane. That's the big idea. Model the process. Highlight the essential elements in a model like this. Oh, that's hard. Can I create a tangible model? Somewhere there should be one, if I do not forget it. Okay. Make a model. Show the idea, the angle, the projections of that line on a plane. There are many ways to establish the equations. Ways that are resonate with calculus students, ways that resonate with school teachers. But anyway, if we spend some time and look at the relations, every curve, the cone, the hyperboloid, and the other cone, they have their equations. I had fun doing this. Now, go back to GeoGebra, and you can test your equations. Do they all come together nicely? The game is not over yet. A cube is a cube because of three big ideas: vertices, edges, right? Faces. And if we adopt a minimalist perspective on things, how can you minimize a cube? Well, perhaps you can do that. Somebody did it using wooden pieces. I just decided to make a 3D model. You need 8 vertices, 12 edges, stack them together. Took me a while to figure out the angle, but that's fun. It's a little bit of high school algebra too. And then we have something like this. If you get a piece of wire, you can actually spin it. They all have holes. One teacher told me, you can actually run a long string back and forth and back and forth, and then you have all the face diagonals, and then you have all the major diagonals. That's great. I want that kind of model. Start from this random string all around, like a lanyard or something. All right, so that's a hyperboloid. Going back to a general case. So let's take a circle, something like that, or a cylinder, and then rotate a little bit, and make a lot of copies in space. You get a pencil holder. That's it. That's what I made a while ago. It can hold 48 pencils. Great desktop structure for math teacher or any teachers. You can dispense pencils with that. And kids are going to ask, that's a strange kind of pencil holder. Perhaps we can make it a little bit smaller. Take one and make a lot of little holders like that. Some have a bottom, others don't have one. It's just the basic idea, stretch it, sell it for $2 for fundraising, I'm not sure. But it's a nice shape. Now you have a curve, and also you have the pencils, showing that all these slots are straight lines. Well, when I saw kids trying to put marbles in in the slots. I said, well, perhaps, where had the big one? Oh, perhaps you can redesign this pencil holder and really allow the marbles to get in and put 2 caps on it and put 2 donuts at both ends. You get something like that. And you're okay, you have I don't have a name for it. It's, I call it the infinite marble track. It goes round and around and round and around. Or perhaps you can, well, it goes clockwise. Make a mirror image, you get a section that's counterclockwise. Marry them in space. You have a very tall, I don't know what shape that, but it's a nice pencil holder. Play with it. When you print it, it's mostly hollow. The game goes on. What else can we do about the cube? It's all started with spinning a cube. Something that's very common, extremely common in mathematics, right? Babies play with letter blocks. How much math do we have in a cube? That 3D printer is a cube. When I showed that to a group of 4th graders at Lewis School, those children tell me, the 3D printer just rises the shape. That's exactly what it does. It rises that shape. There may be more we can add to the list. Just, as I said, just playing with ideas. Take one, allow it to grow, and share, and come back and do more. And I guess you know who the person is, right? You did reach out to teachers. We did take things to children. This is in Puyang, a summer camp with the kids. And kids actually can build that structure. And look at their smiles. All right. Atomic solids. These are the things that are infinitely beautiful. There's so many things you can get out of this. So this is the recent design. I was looking at the gauge with the bottles. What can I do about these things? We're wasting so many plastic bottles. Can we do some math before we recycle them? So here's the story. Well, one day I wanted to play with this. How can you make a dodecahedron? Everybody. How? Get a pentagon? But how can you wrap it around? Even if you know the dihedral angle, how do you design it? If you use like a straws, those straws you drink water with, we are just making a model that's very loose, not exact. But how can you do that? In design environment, it turns out it's pretty easy. Well, I just had to go back and review what is the dihedral angle and how is it related to the extruded angle, which Autodesk uses. When you extrude something like this, there's an angle between this perpendicular and this arm. That angle is to use a negative value, so you extrude inside. You take this one and push it up. As you push it up, there's an angle. You can, as you go up, make a little bit turn. That angle is called the extruding angle. So I had to make something like that to show myself and others. That's the extruding angle here, this one. That's the dihedral angle, and that's the right angle. So for the regular dodecahedral, platonic dodecahedron, it's, in this case, negative arctangent 2. You take 1/2 of that. All right? You do it. You can do it very easily. Take one, do it. Guess what? All these things have symmetry. Once you have one wedge, just wrap it around. You can use rotation, or I like reflection. Just mirror it around 12 pieces. That's it. And you get pretty much a model that you can build anything around it. So slice it in half and kind of highlight the inside of a dodecahedron. There's a cube inside. Very easy. Right? If you have seen it, it's very easy. What if I have not seen it? You are trying to convince me that there's a cube within a dodecahedron. Look at all these like face diagonals. You can make one. Right there. Or you can see I made a lot of cups for outreach, open house and other things. Put a straw on it, and then it really works. Entertain kids. I have you talk about, hey, what can you do with math? And then, well, go back to the minimalist perspective. I want to have these vertices. I want to have these edges. But then how do you design the angles there? These angles are different for each platonic solid. And that's a little bit of algebra 2 plus, I think. You can figure out using real models. Once you get one correct, all of them are going to come together. That's the beauty of design, which allows you to take something small and grow it. Right? You have a big model here. I also discovered something I think I knew already. It's all the platonic solids are similar to each other. If you want a smaller one, you don't have to change the vertices. You just need to take 1/2 of the edge and use it, or double the edge.
So these elements, you print it yourself, right?
Yeah.
And you design them also
Yeah,
yourself?
everything from
Like,
scratch.
I cannot get it on Amazon?
No, you can just send me an email. I have my.
Send everything.
Yeah, seriously, I'll
$10 each.
Thanks to Fanny from the SIU Foundation. All right, so we do send a lot to the schools, and through SIU Foundation funding the grant I wrote last year, and also the STEM Center is funding the resources. The materials are not expensive, just few ounces, but we want the ideas to spread. We want the kids to know what math is. It really does not take much to print this. Why? Make a copy and paste it. That's exactly what I did. The power of mathematical thinking and mathematical. There used to be like a journal called Recreational Mathematics. It's not being published anymore. Something like along that direction. I think we need to go back and revisit the recreational nature of some advanced math. Start from scratch. Slowly build the math. Math, I think I know, but a lot of times it takes a fresh identity as you play with it. All right? So now let's make a buckyball. The dodecahedron is the simplest buckyball. Triangulated. Okay. All the vertices are on the same sphere. That's easy. How do you do that? Oh, you just shell it. The word is shell. You kind of reach your hand inside the pumpkin, and just remove the interior part. And in the design world, there's a command, something like a hollow or shell. You shell it, you get something like that. And then, okay, so much for the dodecahedron. One day I saw this gateway bottles. I said, those caps are interesting. I want to design one. Circles, I think I know already. Thread, I know already. I sliced 1.5 and did some basic measurements. After a few experiments, I was able to recreate this gateway bottle cap. They do have an industry standard. I know every bottle we use today, they have specific, very, very specific parameters. You can find the document online. They're all free. The bottling companies, they have standards for it. But I just start from these bottles. Measurement, basic geometry, right? And this iteration. We can never get things correct when we try it only for a few times. That's the story. And then once I have the basic thread and the what's called the shape, the circle, you can do anything with it. You can make a bottle, aquarium vacuum. Just slice off this and screw on a bottle cap. Get some the tube, and you can vacuum the aquarium at the bottom. Okay, or you can put some tubes around and then make a hummingbird feeder. Just have fun with it. right? Like what you can do with origami. You never know how many origamis the Japanese scientists and artists have created over the centuries. How many? Thousands, right? So inexpensive, so mind-boggling. I just love it. Every time I see origami, I just want to try. All right? Now, you can drink from those bottles. Some waste of plastic, though. But then, the question, what if I wrap this thing around a dodecahedron? Well, initially, I put them outside. Yeah, you can put them outside, but it's really hard to print. Because you can't print things, you need to use extensive support. But then the kid suggested to me, you need to put them inside to make a big cap. I said, why did I not think about it in the beginning? Put the caps inside. But then, you always have this bottom layer. You still have sometimes hanging there. Now, what if you make it a cone? The cone can support itself. So you take a circle and extrude it, so it's not completely flat, but it's a cone. It saves plastic, and it also provides that structure, the cone. Yeah. Very interesting, right? So see if it works or not. Put the bottles around it. We have a lot of soccer players who drink a lot of Gatorade these days. Collect them. Yeah, that's interesting. But something's emerging there. A lot of triangles are emerging. How many triangles? A lot. Count them. What if I design? Somebody told me to ask this question. What if I design an adapter for the bottom, allow it to snap onto the bottom? Look at the Gatorade bottle. It has some kind of groove there. So I did, and there's a measurement with the help of the kid. And you put them all around. Why? You want to highlight the vertices. Now, we all have rubber bands, right? Teachers. Put them around. How many rubber bands do you need before we get started? 12? 24? How many? Or something. Each bottle is connected to 4. Each bottle is connected to 5. But we have 12 bottles. That's 60. Yeah, 60. Do you really need that many? That's good thinking, but you are counting each one twice, right? So even little kids can somehow figure this out. Each rubber band is shared. Well, actually, you can, because it's virtually shared. The two of them divide by 30 rubber bands, right? Okay. And that's playful. All right. Having done the dodecahedron, so I said, well, why not complete the whole set to atomic solid? So I like that because it's something I did first. Yeah, that's relatively easy. It's the same idea. Just to figure out the dihedral angle and the extruding angle and define it. Use a variable. I use that extrude angle, so you can change it any time. You have the cube and octahedron. So that's what we get for a cube. I don't have a big one. So I think it's pretty expensive to make a model like that using wood. Now those Gatorade bottles are serving some mathematical purposes, or teaching purposes. Octahedron versus the cube. They are duals of each other. Now how do we teach the duality of these things? Or do we even want to teach children, even K-12 children, about the duality between these shapes? Perhaps yes, perhaps no, depending on the. But nonetheless, it's an idea we can somehow take to, I say, 7th grade or 6th grade math class. That shows the duality. The vertices become the face becomes the vertex, and going back and forth, back and forth. Yeah, we can draw pictures, but pictures do have limitations. I mean, I did not have this maybe a month ago. It just all started with interacting with teachers and children and looking at the things around. All right, that's the tetrahedron. A moment of reflection. All right. So I made a mistake. When I when I was making this thing, you take a cap and you put it all around, right? Each face has one. I think I like reflection. I just made one wedge and reflected all around. Guess what happened? When you reflect a bottle, the bottle is the bottle, the cap is the cap, the thread is reversed. I could not screw this bottle. You need to design a left-handed bottle, right? So most bottles they're right-handed. That's exactly what happened. So with the dodecahedron, 4 of them are fine, or the other 4,
Oh boy.
they're counterclockwise.
You have to reflect the bottle.
I did not think that I was ignorant of that. I should have known better, but then just what happened. And with the tetrahedron, I did the same thing. I started with 1 and reflected the other 3. So except for the bottom one, all the other 3 are reflections of the original one. So there's only 1 that works. This kind of symmetry creates problem and also affordances, right? It allows us to do a lot of things. It saves time, builds mathematical insight, but it creates problem if you're not careful. That's what I learned. All right. That's a lot of playing around with toys, things that are everywhere. Perhaps we can do more. Perhaps we should stop. Or maybe we can start a conversation about how to support children or college students at all levels. Right? Build something that you can make a profit on, your educational value or real monetary value. I don't know. You may be able to design something. So play with it, and I have a lot of designs there. I'm close to 180 now. Most they are, I call them math arts, because I don't want to scare people away. It's art. Everybody can do something about it. But then eventually, I really want to bring the math back to the conversation. The Thingiverse page there, I think it's also cloned in France. Somehow we ask for permission. Say, okay, these are educational designs. Feel free to share them. Share them. Well, I've had help over the years from a lot of people, seriously. And you can do this kind of work with the support of the teacher and people in this department and elsewhere in the community. I make mistakes all the time, of course. These are the exciting moments when you have a student who's trying to get a job. Say, hey, I'm using what you taught me. Those are the Pythagorean theorem models we designed. And others too. They ask questions. All right. Any questions? Thank you for. Yes.
So you mentioned a couple of times that this is very inexpensive. I know that once you have the 3D printer, basically the only cost is the maintenance of the printer and the filament.
Right.
So an object that, say that marble machine right there, how much would that cost?
This one?
Yeah.
I would say for filament, you get 1 kilogram, 2.2 pounds about, for $20. So this is about, I would say, 3 ounces at most. I always print at an infill rate of less than 5%, unless I have to use a solid infill. So this is like 95% or maybe 98% hollow. So what we are interested in is the shape for mathematicians, right? Not the inside. So that's why it's very, very light. It floats.
So it floats. A floating polyhedron. Oh my gosh, you'd have something really suspended in the midair if you had just like. Oh my gosh, imagine buoyant polyhedron just floating under the waves like in a pool. You just swim amongst polyhedron. That'd be hilarious.
I think the ingredient, the most expensive part ingredient is your imagination. Or maybe imagining possibilities together. Let's all sit down and imagine this, what we can do and try it. creating prototypes like this, I mean, these are not marketable, but they just educate math models. It used to be very expensive. You spend tens of thousands creating the first model, but today, I guess, tomorrow, if you have a model, tomorrow morning you get one.
It's somewhat time consuming, right? So how long
Yes.
would it take to, say, print one of them?
Good question. Okay. This one takes 9 hours to print, but then it depends on your machine, the speed, and the quality you want to have. You can print at a higher resolution, which means that very thin layer. It's going to double the time, but then you get a very smooth, shape, surface. Or if you just want to have a model, lower the resolution, and you get it done in a few hours, 2 hours. Another one is for teachers. Size it, scale it down proportional. If it takes 8 hours to print this one, if I cut everything proportionally to 1/2 its diameter, 1/2 its height, how much time do you think it's going to take? This takes 8 hours to print. I scale it down to 50% of the original.
1 hour.
1 hour. That question is a great one for children, teachers, right? Because we are talking about 3-dimensional processes. Most children have to see, to experience that. Why 1/8? Why is it not 1/2? Well, you can try it. So that can cut down the time dramatically from 8 hours to 1 hour, right? So you get a tiny model. So that's why I have these little things. It's a cube spinner. You can do things that are almost impossible to make. Using your mathematical eyes, you can go inside the shape and design something and come out. That's a cube, and you just draw a circle along the major axis and then allow the circle to cut it, and then leave some space there and print it out. It spins. Oil it a little bit, and of course that's printed at a very, very low infill, 5%. If you can try 25%, pretty solid.
Technical question, right? How often do you have to actually repeat the process because something during the process gets reshaped or something?
All right, good. That's a design issue. We need to design things that are printable. There are things that cannot be printed, but if you slice it, and it can be printed with maybe low failure rate, sometimes the part will come off the bed because you have to stay there. And if it's, really, really bonded well with the bed, you can't pull it off. That's how I cut myself. Use protective gloves when you remove parts. If you use a knife, it's very dangerous. Well, not always, but wear gloves. But if there's not much contact with the bed, like this, and after a few minutes it comes off because there's no stability, right? So you put it here like this on the bed, or it's going to be fine. And also machines are machines. Sometimes machines run into problems. Filaments is not always pure, and there are things in the filament that can get the nozzle clogged, and when that happens, you get a failure. So I document all the failures, a lot of them, and sometimes we'll review the failures and learn about. It's an engineering problem, sometimes it's a math problem. You did not design things right away. Things are not spinning because you did not leave much space between the parts, right? How much is too much? 0.2 millimeters, 0.4 millimeters. What is 1 millimeter? Ask yourself and ask children, what is 1 millimeter? Some say this much, some say this much, until you come to the design world. 0.2 millimeters in 0.1 makes a difference. Measurement and other things.
I'm going to actually echo that. I find it really entertaining whenever I'm going anywhere to ask somebody what a square inch is. And half the time they struggle and they have no idea that it's actually literally just a square. Some people say, oh, it's this distance. And it's like, square inches are squares. And then once I explain it to them, they're like, oh my gosh, has that been what I've been doing this entire time? And nobody told me. The way to measure the world is vastly undertaught, I think.
Yeah, so. I think we tell students this there are 3 feet in a yard, but how long is a yard, right? What do you mean when you say double double the cube. Proportionally, or do you mean double is volume or double is linear measurements in all three dimensions? So this is something to clarify. And also, most children have not had experience with this like a tiny measurements, nanometers. What do you mean, right? We know gigabytes these days because of USB drives. But what do you mean by a nanometer? This much? This much? We have to really imagine it, right? But here, this is something that I think is friendly for school teachers, if all children can feel comfortable about this kind of measurements and splitting things back and forth, go into the shapes and imagine something can come out, translate it into algebra, and back and forth, develop some confidence with math or STEM in general, I would be very happy. A lot of times, me as a teacher, I just learn so much when interacting with the people.
I had a student chide me after an exam because I didn't tell him how long the yardstick was. He didn't really know that the yard is a measurement.
It's a lack of experience for some.
How many schools have access to 3D printers?
I would say most schools have one or two printers these days, unless the school is really, really far. Even in rural areas, because there's kind of value for these rural schools to bring some technology into their faculty. The challenge right now is to how can we get the printers to work for educational purposes. A lot of times they sit there on the desk because people are concerned I might break it. It's pretty tough, and it's a great opportunity for us to teach teachers and children about the importance and the beauty of mathematics. You understand a 3D printer, and you understand a lot of, I would say, K-12 math.
Do you encourage your students to come up with designs?
Yeah, they can do something.
AutoCAD or something, right?
I use Fusion 360 because it's free for educators.
What's it called?
Fusion 360. This one. Yeah, Fusion there. This is a new software environment. You can go to Autodesk and find it. I think it's something like this. Autodesk Fusion 360.
Fusion.
Yeah. It was released in 2017. Before that, people were using, high school teachers use Inventor and mostly Inventor and AutoCAD. But this one is educator friendly. The learning curve is no steeper than Cinderella. Because start with something like a bottle. Design a coffee mug. And you take a circle, go up, right? Or take something. Do you want to go up or do you want to go rotate? Either way is fine. And then you design a circle for the handle, right? And kind of you take things to the other plane. So you always are, hey, talking about the planes, floor, that wall, and that wall. We have a basic model here. There's nothing more common than 3D printing, and there's nothing more difficult if you do it on paper.
So the last question is, the seminar will end together with the ending of the printing of the thing, right? So
no.
We need another 2 hours.
We'll have to leave it here or stop it. Guess what? Great question. A lot of time, if we stop the printing process unexpectedly before you complete, you get some amazing results. Because it's just a cross-sectional cut of the shape, right? You never know. I failed this one, and the shape was so beautiful. It's like, well, take a cube. If you slice it, imagine in the middle, there's a hexagon here. Look at the center pieces, right? And you cut it in half, you get a hexagon. You never know what you're going to hit upon when you play with it. A lot of surprises.
Don't shoot.
You can do it. Okay. I do have models for that. I also designed a handful of ways to trisect a cube. Trisecting a cube is so interesting. And you can go to the Thingiverse page and find those. Or if you want a physical model, send me an email. I'll make sure I send the model to your office. I mean, again, mostly it's hollow inside. We are using electricity, of course. SIU provides that, not much. The material and donations, and I think there's another conversation about
Any other questions?
engaging people in doing some math.
Do you have any questions for Lingguo? And then let's thank Lingguo again. Then we have a refreshment on the third floor as usual, and then we can listen to him for more. Can we ask around?